Thank you for coming, and welcome to the newest branch of Maxar, otherwise known as Hacker Dojo. My name is Eric Wall, and I am the chair of the San Francisco section of AIAA. And AIAA is the world's largest professional association related to aerospace and other similar sorts of technologies. And on behalf of AIAA, I'm glad to welcome you all here, and we are very happy to put on this presentation for you. If you would like to hear anything further about AIAA, I'm around after the presentation for a little bit, and we also have some other council members here, including Rick, who's running the AV side of things, and Prasad up here, and Sina over there. And we also have one in training in the back, Ladan, who can also help you out a little bit as well. Anyway, so let's get going with the main show. Pull out my glasses here because my eyes are, going to be that age. Okay, so anyway, our speaker for tonight is Dr. Ian Johnson. Dr. Johnson is a principal engineer at Maxar Space Systems, where he leads propulsion work for several bipropellant and electric spacecraft, including Psyche, which is the one that we're here to learn about tonight. He received his PhD in aerospace engineering from the University of Washington in 2015, where his research focused on integrating an alternative propellant pulse plasma thruster into the high-power helicon thruster experiment. He joined Santa Clara University this year as a lecturer in the mechanical engineering department. Please help me welcome Dr. Ian Johnson. Yeah, whichever way. Sure. Jump on the stage. Come from the other side.
Rick, you stand up here? Huh? You stand up
just going to sit down here.
Oh, that's very exciting.
I got a good view of the slides.
I like it. Good evening, everybody. Thank you all for being here. It's cool to see so many people. Let's see if this works. Break
We like skiing.
I think we're just going to leave it like this. I think that's a better option. Now all the pages disappeared.
Oh, there it is.
All right. So, my name's Ian. I'm on the propulsion team. Joined this program 2017. This was a small Class D science mission for NASA that took a small army of people to make work. A couple pictures of a few of the groups up here. Fortunately, Maxar, located just up the street. A good number of the people who worked on the program are still at Maxar today. Some of us in Psyche meetings today. And some of those people showed up tonight. And so this was not a one-man show. This was an army of people at the last possible minute helping to solve all the problems that I made and other people made. And so I just wanted to ask real quick, if you're in the room and you did anything on Psyche, from a 1-minute conversation to working on it for a decade, if you could stand up real quick and just be recognized from the other people here. So that's most of this table. Round of applause. A team effort, and really just a pleasure to work with all of you and the whole crew. All right, so Eric, I'm gonna need your help. Somewhere, those YouTube videos were on here.
That's on Chrome.
Chrome's not open? Oh, maybe it is. Oh, there, yeah.
No, wait. That's right.
Oh, there we go. Perfect. Thank you. All right. So a few of the folks put together a pretty good video talking about what we were doing. Want to share it? Let's see if the audio works.
At the end of the day, it's always a philosophical question, right? Why are we in this universe?
Space just inspires everyone of different backgrounds, different nationalities. So I think it gives, in a sense, this kind of hope for humanity.
As human beings, we're not exploring. What are we doing?
It's extremely difficult science and technology, but it's possible.
My name is Luis Dominguez, and my job is to assemble all the different components for the Psyche spacecraft.
I'm Julie, and my job is to propel the Psyche spacecraft to a metal-rich asteroid.
My name is Christina Hernandez.
My name is Vina Shrikandamurthy.
And I'm making sure that we built a spacecraft that's ready to explore a metal world. What's really exciting about Psyche being a metal-rich asteroid is we haven't yet had the opportunity to explore a planetary core, and that's what we actually think happened to Psyche.
There is a theory that this metallic asteroid may be very closely related to materials that made up the core of our own planet.
It could have been the remnant of a planetary collision billions of years ago in our solar system. All that's left is the metal-rich remnant.
Scientists hypothesize that by studying this asteroid,
We think that would give us a lot more insights on what our actual planet is doing here.
So this is the Psyche spacecraft. We're basically looking at a spaceship that's going to space.
And welcome to High Bay 2 at JPL. We pulled together all the different components that everyone's building, and so this is where we control the Psyche spacecraft. How things happen on board.
this is where I work on the low voltage power supply for the Psyche mission. It's pretty exciting to watch something that we built with our own hands,
To see something that you've spent years on.
launch, and a couple of years reach Psyche and send back science data.
We formed a really, really critical team.
The diversity of skill sets that each one of us in our community brought to the team to make this kind of impact to society is what inspires me to be an engineer in the Space Exploration Center.
All good people. Minimize it and hope we can find it later. I definitely will not be able to find it later. All right. Okay, so I work for this company called Maxar. We're right up the road. We've had a bunch of names over the last 50 years, but basically we've been doing the same thing. Building very large spacecraft that work for a very long time and work exceptionally well. We do it, I'm going to argue, better and cheaper and faster than a lot of the competitors. There's a reason we've been around for a long time. We worked with this really cool planetary science professor at Arizona State University, Dr. Lindy and JPL, for this mission where they said, it's got to be low cost. We need to find something that we know will work, has flight heritage, we can get it cheaper. And they looked at our communication satellite and said, we can make some minor modifications to that to have it go to this very different place. And so that's the program that we all won in 2017 when I joined the program. And since then, for the last 6 or 7 years or so, there's been a bunch of us that have been working on this at Maxar and JPL, and we'll talk more about this later, but in the last couple of weeks before launch, basically all of NASA coming together to get us onto the launch pad. We launched Friday the 13th in October of last year. It was about 7 months ago now, just over 200 days. Mars flyby 2026, and then arrive at the asteroid 2029. So this program, we're about halfway. We're about halfway there from 2017 to today to 2029. So today we're just going to talk a little bit about the Psyche mission and the spacecraft, some of the successes we've had, and some of the very large setbacks we had to figure out. So the mission is to this satellite called Psyche. It's very confusing. The spacecraft's called Psyche, the mission's called Psyche, the asteroid's called Psyche. It's about 200 kilometers in diameter. Originally, we thought it was all metal. Now we're thinking it's mostly metal. Nobody really knows. That's why we're going in the first place. The top objective, the top science objective, was to figure out if this largely metal object was an exposed core of a previous larger structure, a planet of some type? Or is it something else entirely? Having worked now a few NASA programs, it was really nice that the top objective never changed. From day one, we were always trying to do the same thing. A welcome change from most other programs. So the science objective is why we're going. There's a large science team. I really don't know anything about that. What I do know is the technology demonstrations that we put on here. This was the first use of this very efficient electric propulsion system beyond the orbit of the moon. And it was also the first use of a very cool laser comm system, which is just setting records left and right. Well, every single Monday, weather permitting, for transmitting data back at speeds way higher than anything we've done before. So Psyche's orbit, shown here in red, it's in the main asteroid belt. It varies between 2.7 AU, Earth distance to the sun, to 3.3 AU. So Earth is at 1 AU, and this is about 3 times further away. It's dramatically smaller than the moon. It's 1,000 times smaller. The diameter is 10 times less. The gravity is about 100 times less. It's a very, very small body, and we're trying to get an orbit around that, which requires a lot of velocity change to the spacecraft to do, because it's not a large body with a large gravity that'll pull us in. We basically have to do all the work ourselves. Schedule for the mission, 2011, back when I was in school, Dr. Lindy at ASU had an idea. She said, there's this thing out there, we discovered it a while ago, we've never been to anything remotely like it. So she submitted the idea to NASA. NASA then goes through their process. She works with JPL. JPL has a lot of people who work with Maxar quite a bit. So JPL selected Maxar. Between 2014 and 2016, ASU, JPL, and Maxar worked together to put this proposal together to NASA headquarters. That was awarded along with the Lucy mission, another asteroid mission, in 2017. And that's when things really kicked off. That's when we got into the requirement review phase and the design review phase, starting to build, starting to test. Went on forever. Right in the middle of that, the world shut down from COVID, which did not help matters one bit. That was right about when we shipped the spacecraft down to JPL. Just an absolute mess. So all the pictures, they're kind of in the middle. Everyone's wearing masks. You got people calling in from the living room. It was just a mess. Then we get to 2022. That was the launch date that was proposed. I remember I was sitting at a bar in Boston with Faraz over there, and I get a meeting invite on my phone. All hands meeting tomorrow morning, 8 a.m., cancel your other plans. I'm like, wow, that can't be good. I think that was June. We were supposed to launch in September, and it came together and said, we're not going to be ready. We're going to slip the launch date. So it slipped about a year, and then we got to 2023, and it slipped a little bit more, and we finally got off the ground in October. And so we're currently about 6 months later. There's a lot left to do on there. We're about halfway. There's a lot left to do. Mars flyby in a couple years, arrive at Psyche in 2029, and for the science team, that's when the mission really starts. So where are we right now? There's this cool website that I have booked on my computer, Psyche_now, and you can look it up and it'll tell you exactly where the spacecraft is. And my friends on the orbits team say it's pretty accurate, to within about a week or so. We are currently 18 light minutes away from Earth. So that means when we're down in mission control, sending a command, it takes 18 minutes to get there. The spacecraft does its thing, and it takes 18 minutes for us to find out if it worked or if it didn't work. It's an absolute nightmare. I hate it. I don't know how the Voyager team handles this. just a mess. So we launched here from Earth, October 2023. We had a 100-day checkout phase. It was very interesting to watch the NASA process work. For Maxar, we usually get 2 days to check out the spacecraft, maybe 3 days if we're lucky. Then we went into the cruise phase. That's the gray background on here. And we're about a third of the way through that first kind of cruise thrusting phase. We'll make it about halfway to Mars, and then there's a large, just kind of float around in space for a while before that flyby. That'll give us a pretty large speed change. And then we come back with a very long thrusting phase where we very badly need the thrusters to work. And that'll end just before we get to the asteroid, 2029. And then the asteroid spends 3 years, two years, making its way around the sun, varying between 2.7 AU and 3.3. And we spend that time going to lower and lower orbits to try and get closer and closer, take better pictures, take better measurements, whatever it is the science team does. So for the science world, determining whether Psyche is a core or if it's something else, unmelted material, who knows. For the internet, there's this cool metal rock out there that we could mine and make a lot of money off of. And there are a bunch of companies, some of them still in business, some of them not, that are very interested in this. So there's the science objective to this, to learn, could this be a core similar to Earth's core? And then there's the asteroid mining community that's very interested in this mission to learn more about how that industry could function. Oh. All right, let's see if this plays. So a cool animation put together by the science team showing what may have happened. May have been a planet out at the asteroid belt struck with something. That core solidifies, generates a magnetic field. Let's play that again. Starts to get struck by other bodies, hence all the craters. We don't really know why the asteroid belt is there at all. It may have all been one giant planet once upon a time. And this may have been the core of that planet. The planet may have been a lot like Mars or Earth and tell us a lot about part of our world that we can't get to. So as far as the science goes, Maxar's job was to integrate all these instruments that were built by someone else. So we have the cameras over there on the left, we have the magnetometers in the middle, and we have gamma ray and neutron spectrometers to tell us what material is coming off the asteroids. Being a propulsion engineer, the magnetometer is the only one that I'm really interested in because we produce really strong magnetic fields. And those magnetometers can pick up those fields. And when the science team wants to use that instrument out at the asteroid, we have to turn the prop system off. The secondary payload, not strictly necessary to get to the asteroid or the science about the asteroid, but for NASA missions, you can't just do one thing. You got to get funding from a bunch of different places. And one of those funding sources is this technology they've been working on called the Deep Space Optical Communications Network, DSOC. And this thing, it was such a pain to integrate onto the spacecraft, but it is so cool now that it's working. The ability to transmit more information faster than we've ever been able to do by orders of magnitude is just amazing. The team uses it every single Monday, assuming the weather is cooperating in Southern California, which most of the time it is. Yeah, mounted right there on the side of the spacecraft. Took a ton of effort to get that on there, and I'm really happy that it's up there and working. So the spacecraft that we built, that my company built, if you Google what does a communication spacecraft look like, you're going to get a bunch of cartoons that look like this. Really big solar arrays, because you need a lot of power, and really big antennas, because you got to beam stuff back at Earth. It hangs out in space. Hangs out over one point in space, points back. In reality, they look something like this. Our customers are people like SiriusXM Radio, DirecTV, Intelsat, EchoStar. The spacecraft, they all kind of look the same. Some of them are massive, like the one in the top right. can judge against the people standing there. Some of them are smaller because they don't need as much capability. They want to be a little lighter. They want to be a little cheaper, such as the one at the bottom there. But up on orbit, they all roughly look the same. Giant solar arrays, big antennas. So this is what we build for GEO, and compare the size of this to the people standing there. And then you go to the Psyche spacecraft. The smallest spacecraft we've built of this class. Much, much smaller than the Geocom spacecraft that are up there, but generally the same thing. It's a box-looking structure. It's got big antennas on one side, or it's got big solar arrays on each side, and antenna sitting on top. The core of this is very similar to what we've built before. And that's why the heritage is there and the safety is there. Now, the most important parts of the spacecraft is the propulsion system. Not everyone seems to agree with that in the company, unfortunately. So there's two propulsion systems. One is supposed to be the simplest prop system you could ever imagine. It's called a cold gas thruster. Up there in the top right, you got a little valve. I can hold it in my hand. It costs more than my car for some reason. We have 12 of them on the spacecraft. There's one on each corner on the top, one on each corner on the bottom, and then 4 for roll capability on bottom, so 12 total. And then we have these highly efficient Hall thrusters that use the electricity from the solar panels to generate thrust. And we have 4 of those on the spacecraft. They're built by a Russian company called Falcon. We've flown them on a whole host of spacecraft. So to us, it's very high heritage. We have a lot of experience with them. This is the first Hall thruster mission that NASA's flown. So it was very new to them. They're learning a lot on orbit right now. So as far as propulsion systems go, things kind of fall into 2 broad classes. You got the old school chemical propulsion, reliable, it's not going away anytime soon. 3 broad categories: cold gas, where you literally have a high pressure tank, you got a valve at the end, you open the valve, stuff goes out one way, spacecraft goes the other. Then you have liquid. This is what most launch vehicles use, what most on-orbit spacecraft use. You have 1 or 2 propellants on the spacecraft, you open valves, you mix them together, you get a big flame that comes out. That's what's being shown in the bottom image there. Been around a long time. And then you have a solid, which is what most amateur rockets are. Fuel and oxidizer combined together. A lot of high NASA heritage. Psyche has the cold gas system. A lot of propellant can come out very quickly, but the propellant comes out slowly. The propellant velocity is slow. So you go through a lot of propellant quickly, but you don't generate that much impulse out of it. You can't go very far with it because it's coming out so slowly. A couple kilometers per second, so slow is a relative term. Then on the right-hand side, you have this newfangled electric propulsion. It's been around for 50 years. A little bit of propellant comes out very quickly. So instead of a kilometer or 2 per second coming out, it's 30 kilometers per second or 40 kilometers per second. Comes in a couple broad categories. The Russians, 50 years ago, invested heavily in Hall thrusters. The United States invested heavily in gridded ion thrusters. Past NASA missions used the gridded ion thrusters. They're very efficient. The thrust is very low. We like Hall thrusters more. The world is transitioning over to Hall thrusters in my view. They can scale up to very high power. You can get very high thrust out of them. The velocity of the particles coming out isn't that bad. It's much better than chemical propulsion. It's been a very effective propulsion system for us. We really like that NASA's getting more into it on flight programs. We think a lot of good things there. But the one big risk for NASA was they've never flown that before. But they were able to buy down that risk by coming to a company like us who flies them all the time. And so they were relying on our experience to buy down the risk that they had. So I said earlier on, in 2017, there were 2 asteroid missions that were chosen, Psyche and Lucy. The 2 missions both go into asteroids. Both science Class D missions, but very different. The Lucy mission is going by 5 asteroids. It has multiple flybys of different asteroids, but much like the New Horizons mission to Pluto 10, 15 years ago, might be dating myself, might have been more than that. It's a very short duration pass. They're only close to it to be able to take high-res images for a couple of minutes. And because they don't have to go in orbit, they don't need a big change of speed, so they can get away with having a less efficient propulsion system. So they selected chemical. High thrust, low propellant velocity, less ability to change the velocity, but that's okay if you don't need to get into orbit around something. Psyche was different. Psyche needed to get to something very far away, and then it needed to get in orbit of that something, and there wasn't a lot of gravity from that asteroid to help. So it needed a propulsion system that could apply a lot of impulse. And that's where electric really comes into play. We have low thrust. Our thrust is nothing. It's like getting hit in the head with a couple pieces of paper. You're not going anywhere quickly, but if there's no resistance, there's no air resistance, there's no gravity pushing back on you, you can get up to very high speeds because you can do that for years on end. High propellant velocity, that means you don't have to use as much propellant to get somewhere because your propellant's coming out very, very quickly. Unlike Lucy, we're only visiting one thing, but we're spiraling into a very, very low height. And so it requires a lot of impulse that chemical propulsion simply can't do. This mission wouldn't be possible with chemical. On the other hand, the Lucy mission isn't going to be possible with an electric prop system because it needs to have these big kind of change of directions quickly. And so 2 different missions, 2 different propulsion systems. It's not like one is better than the other. They serve different purposes. And Psyche just needed to use this system. I considered deleting this slide. I got convinced to leave it in. So the question is, how do these Hall thrusters work? How does this thing work? 5 broad steps. You get neutral xenon. If you've never heard of xenon, it makes your voice go deep if you inhale it. And then it's heavier than air, so then it just stays in your lungs and you got a serious problem. It's also incredibly expensive. Incredibly expensive. We loaded millions of dollars of xenon onto this spacecraft. Neutral xenon comes in, it goes into the anode, which is at a couple hundred volts. It goes into the cathode, which is over 1,000 Celsius. That cathode, because it's so hot, starts emitting electrons, negatively charged electrons from those xenons. Those electrons get trapped by the magnets and they start to swirl around. That swirl motion is called the Hall current, which is what gives the thruster its name. Those electrons that are now trapped by the magnetic field collide with the slow-moving neutral xenons coming in. You get an electron that slams into a neutral. You get these positive charged ions that come out. Those positive charged ions are accelerated by other electrons. They get accelerated out at high speed. The more voltage you apply between the anode and the cathode, the faster the stuff comes out. The more xenon you dump in the back of the thruster, the more thrust you get. That's not that complicated.
There's a video?
There is no video. There is no video. There should be a video. There is not. Yeah. So we get about 200 millinewtons of thrust. That's tiny. Launch vehicles are meganewtons. The chemical propulsion systems are newtons. 200 millinewtons is nothing. Flow rate, 15 to 20 milligrams per second. That's nothing as well. It's just a trickle coming out. But we throw it out at very, very high speeds, 20 kilometers per second, incredibly high speeds. And we can also fire for months to years. So you can fire for a very, very long time, compared to chemical systems that you run out of propellant after a couple minutes. All right, so we got through the design phase in 2019, 2020. The world shut down because of COVID, and now we have to go build this thing. So this is a picture of the spacecraft in the propulsion lab. The structures team fits the primary structure together. That's what you can see in the background, that big cylinder, a couple decks. They deliver that to us. We put in all the little propulsion bits and pieces before the rest of the team gets their hands on the spacecraft. What you can see here is some of the xenon tanks that are about to slide inside that cylinder there. Once propulsion gets done with it, we deliver it to the main body, and that's where they put on all the little electronics boxes and the harnessing and all that stuff that I don't really care about. We built it up in 2021 and delivered it down to JPL. Looks something like this. Those red boxes on the side are these cool thermal panels that open and close. They're called louvers. They're like windows. Thermal's very excited about them. You can see some cold gas thrusters are on there. We're still working on the electric propulsion thrusters at this time. End of 2021, JPL starts adding all their little bits and pieces on. We finished putting up a couple last-minute pieces of ours. You can see the electric propulsion hull thrusters are installed now. You can see a lot of the science equipment is installed. There was a solar array test. Just a lot of really, really cool stuff. And then once it's built, it has to go be tested. And it gets tested a lot. And this is a picture of it going into the JPL vacuum chamber, which simulates the background of space and also the temperatures of space. Very, very extreme environments. Not a propulsion test at all. Doesn't matter. There's dynamics testing where we shake the spacecraft, where you shock the spacecraft. There's acoustics testing, making sure that the comm system works correctly. Really put through its paces. Early 2022, we were working hard. We were pulling more than 8-hour days, pushing, trying to get there. And then come June, the team got together, said, you know, we're just not gonna make it. We don't have the confidence that we can make it here. The software team got blamed, but we were all behind. And so that happened in June, so that was a rough couple weeks. And then about a month later, they announced, the mission's not canceled. We're gonna launch the next year. They announced the date, and we kind of got going again. So propulsion got to stand down for a while. And then August 2023, we fly down to Florida to load propellant. There's the nitrogen propellant for the cold gas thrusters, about 50 kilograms of that. And then the xenon propellant for the electric propulsion thrusters, about 1,000 kilograms of that got to get loaded on. The nitrogen's pretty straightforward. It's just a gas. The xenon, also just a gas, but the hull thrusters require that to be very high purity. You can't have oxygen, you can't have nitrogen, you can't have little bits of oil and water and atmosphere in there. So we got this whole big contraption to filter out all of that stuff and get the xenon up to high pressure. It's quite an operation. See a few of us working there. It took about 3 weeks to load all of that propellant. It was a good time in Florida. We got done, I think it was August 31st. I think it was a Thursday. And I was having a pretty good Thursday. I was gonna go to Miami for a 3-day weekend, and I was gonna fly back, and we had like a month before we launched. I had a really good Thursday. And then Friday happened. And I got this phone call that said, there's a meeting at 3 p.m., clear your calendar. We got a problem with the thrusters. And I think I took that meeting while driving down the Florida highway to Miami. At which point I spent the next weekend taking meetings on the Miami beach about the problem. But credit to the thermal team. They identified this problem in the thermal model with the thruster. That ended up actually not being a problem at all, but it identified the real problem. So this was about a month before launch. That's when you should be coasting, all the major issues are solved, just gotta get it across the last yard line. And this was a hectic month. We spent about 4 weeks nonstop testing down in the JPL chambers. Credit to JPL, they spun up an army of people to go solve this. The entire NASA organization, we were in meetings with people at NASA Marshall, NASA Goddard, NASA headquarters. You know, we'd say, we ran into this problem where our flow meter is a little bit out of calibration. The next day, NASA Marshall had shipped us 3 flow meters overnight. It was, you think of the government as this slow-moving, not efficient organization. That was not the case here. They put an army of people onto this problem. to go fix it. And the end solution, which is now released so we can actually finally talk about it, we were firing the thrusters at a pretty high duty cycle, about 80%, and they were overheating. That added too much energy, too much heat into the coil. And so the solution was relatively simple, just fire them less. So we lowered the duty cycle, we went from 80% to 30%, cut the impulse that we could generate in a short amount of time by half. The GNC team had to go look at that, figure out that they could still do all the maneuvers that they wanted. By the time we got that all sorted out, we needed about an extra week. And so the launch got delayed a week because of this problem. And just credit to that whole team coming together to solve this. Very, very stressful couple days, right before launch. So we finally get done. We're finally done. We hand it off to SpaceX. They encapsulate it into the fairing. That's what's shown in the top right there. That fairing gets trucked from the processing facility to the SpaceX facility where it gets put on top of the rocket. And all right, Eric, I'm going to try and get back to the video. Oh, all right.
T-minus 10,
pretty good.
9, 8, 7, 6, 5, 4, 3, 2, 1, engine ignition. And liftoff. Liftoff of Falcon Heavy and Psyche on a mission to a metal asteroid in deep space to study the building blocks of our planet's inner space.
Vehicles pitching downrange. N1D chamber pressure is level.
Keep the air forward camera. Booster. Beautiful shot there as it goes through the clouds.
So that was about, figuring it out. All right, so that happened about 7 a.m. Pacific. A whole host of us had to be, I'm so excited. A whole host of us had to be on site at JPL at about 4 a.m. before this launch. So you can see the launch down there in the bottom right. And come 7 a.m. in the morning after I haven't had coffee, I wasn't so enthusiastic about standing up and clapping all the time. And so here's a pro tip to all of you. When you're on national television and everyone around you is clapping and standing, you should do the same. I wish somebody had told me that beforehand. I look slightly more enthused in the lower picture. I think this ended up being a 16-hour day or something like that. It was, yeah, the stress continued. But yeah, you can see a picture of the Falcon Heavy launching down below. The cool part about SpaceX, I mean, there's a lot of cool stuff about SpaceX and reusing rockets, but this launched in October. That first stage, the lower half of that rocket, was used to launch a Maxar spacecraft earlier that year. I think it was in July. The exact same hardware. And the exact same hardware is being used to launch Europa Clipper later this year. So it's cool to be part of these things and say, that rocket launched one of my things earlier, and it'll launch another one of my things later. So we're up on orbit. We've been there about 7 months. Things are going pretty well. And we're starting to get some data coming in. And when you're sitting down there in mission ops staring at stuff, and I worked on that. That little thing went up because I designed it to go up. Or you designed it to go up and then it went down and then you gotta go figure out why. So the image on the left is one of the displays we have. It shows the orientation of the spacecraft relative to the sun and the Earth. It shows which thrusters are firing, what position the gimbals and the arrays are on. Some example telemetry we get is the top right. That's power going to one of the thrusters for a firing, looks like November 29th, so about a month and a half after we launched. These thrusters get up to about 4.5 kilowatts of power. Very high, very, very high. And then because we need to test it, we need to go into deep space where there's not a lot of sunlight and not a lot of power, we also have to throttle it down very, very low. Much lower than we have to for our communication spacecraft here at Earth. So that was a big point of emphasis when we were designing it, and super excited to see that it works at that lower power level. The other big thing with Hall thrusters, you got such little stuff coming out that when you're testing it on the ground, the performance of the vacuum chamber that you tested in matters a lot. Even though there's just a couple molecules floating around in the chamber, those couple molecules have a huge effect. So this plot on the right, that was some ground testing we did a few years ago. It's thrust or performance on the vertical axis, and then it's background pressure on the x-axis there. And the red is the data that we took. And you can see we varied the background pressure of the chamber, and the thrust changed. And as you start getting to lower background pressures, the thrust starts falling off. And if you look at that, it really starts plummeting. Like, it's really going down a lot. And we can't test on the ground all the way to zero. We don't have the ability to make a vacuum chamber as good as space. And so the big question is, where is that red line going to impact that vertical axis? And kind of anybody's guess. You could draw any type of curve fits through there. So we take a bunch of best guesses. The NASA team does a bunch of modeling. We came up with a prediction of 250 millinewtons, and it turned out it was actually about 270. So it's performing better than what we planned the mission around, which is really good, really, really good. Not a lot of Hall thrusters have flown from NASA. This is going to help them, figure out how to prepare Hall thruster missions in the future. So there's also a whole host of science instruments that have to get checked out. The magnetometers, these are the ones that interface with the thrusters, so they're the ones that I'm most interested in. But they're also the ones that can detect coronal mass ejections. They can detect solar storms. They picked up all kinds of energy about a week and a half ago from the storms that we had with the Aurora. Very, very cool. They can also detect the magnetic signatures from thrusters, reaction wheels, the heaters turning on, the spacecraft electronics doing things. This plot on the lower right here, the line at the bottom, that's the thruster current. That's how much current, how much power the thrusters are drawing. And you can see these kind of random spikes that we get in there. This is a known feature of the thrusters. They kind of go through these different modes as they fire in. And the cool part about those spikes is they line up where the magnetometers are detecting things. And so the magnetometers can detect the magnetic field changing as the thrusters undergo these mode hops. Propulsion system, we only get telemetry about every second or so. We're not all that important. The science team, they get telemetry on tens of milliseconds. So they're able to pick up a lot more than we can. You can see the kind of the spikes that we pick up, and then on the top, the black, they pick up way more than we do. So they're able to tell us almost more about the thrusters than our telemetry is able to. Then you get the laser comm system, something that I'm excited about and look forward. I'm hoping I get the opportunity to work on more science, kind of deep space science missions in the future, and this type of technology can be part of it. So the DSOC, first off, it's just beaming cat videos down, which I find hilarious. We've spent millions of dollars putting this technology demonstration on there. They loaded up a bunch of videos, and then every Monday they beam the videos back to us. It is comical. But it's doing it at 267 megabits per second. And not being a Comm person, I'm like, all right, that's a big number. 267 million bits per second, that's a big number. Then you compare it to the Voyager spacecraft. We send it 16 bits per second. It's not 16 million, it's just 16. And then it's coming back at us with 160 on its X-band communication system, and then 1,400 bits per second on its high-gain antenna. That's orders of magnitude less. MRO, Mars Reconnaissance Orbiter, that was 2 million bits per second. Odyssey, 256,000 bits per second. This is far higher than anything that we've done before. It's just a technology demonstration on this mission. because NASA needed to show that the technology worked before they felt comfortable enough making it a required operating system on a future mission. And so the propulsion could get more than 1 data point per second if we had this thing actually hooked up. But it's not treed into the rest of the actual spacecraft. It's kind of its own experiment. And I think the last slide here. So this mission is super fun to work. And a lot of credit, as an engineer, I don't say this a lot of credit goes to the managers on the program. And in particular, the principal investigator, Lindy, this planetary sciences professor down at Arizona State, she saw this mission as not just, let's build a box of hardware and electronics and put it in space. She saw this as something to inspire people, to really try and get more people involved in the mission, a lot of outreach. So she got involved in a lot of the art classes and the art department at Arizona State, University of Arizona, other schools. And if you just Google Psyche artwork, there are thousands of college students who, as part of a final project for some class, did something, whether that's a painting or a song or a sculpture, whatever it is, they did something related to this mission. Some of it's good, some of it's questionable, but two of my favorite are on here. The first one that came very early in the mission from 2017, just looking at the Psyche spacecraft kind of riding these waves. And then just right before COVID happened, the humanities Psyche. I don't know, I really like those two, but there's a website down here, just some very, very cool stuff. And it really made this more than just a 9-to-5 job. It was a fun program to work because it felt like more than just a program. So that's all for me. Thank you all for being here. Especially thank you to the Maxar crew who worked on this so hard. A lot of fun. Thanks, everybody. I'd be happy to take any questions, and I'd be happier to redirect those questions to a bunch of the others.
So, first question, how many all thrusters were mounted on the spacecraft?
There's 4 of them. Yeah, 2 on each side.
Do you know the nominal specific impulse of each of the thrusters?
High power, what do we get up to? About 1,800 seconds, 1,750, and then low power, about 1,000. But yeah, it's pretty good. Yeah, I mean, these thrusters have been around a long time. They're not new technology. The Russians were building these and testing them 30, 40 years ago. So a lot of work today on building higher performing ones. But the ones we're flying here are pretty good.
So is a couple questions. Is the total propellant throughput or total impulse, how does that compare to a typical geoconcept thruster?
More.
Yeah.
More.
Okay.
So, well, this just has an electric propulsion system on it. And we're putting more propellant through it than a geocon does. But it doesn't have a chemical propulsion system on it. I guess it has the cold gas thrusters. But because the electric propulsion system is more, it doesn't need any of the chemical.
Right, so the second question then is, for momentum management kind of in mind on the long transit, so are the cold gas thrusters used, or is it all just handled through the floor?
Yeah. The hope is that they're not. They should only be used for safe mode. But yeah, they have reaction wheels that are doing the bulk of the work, and then the electric propulsion thrusters are on gimbals, which can move around. Yeah.
So, how long the spacecraft can orbit
the orbit?
Yeah, and then what will be the final, and it will crash eventually? Or
how close do we?
Yeah,
so,
how close you can get.
This thing about NASA, right? They have a mission, and then they complete the mission, and then they do a bunch of other stuff. And I know people are thinking about what other stuff to do with this, but they're holding those cards close. They haven't told me yet. I think we get down to just a couple hundred kilometers Shane might know.
I thought it was 70. I thought they get down to like
70, yeah. It's really low. And I mean, my guess is if it's working fine and they have more money, they're gonna try going even lower. But as far as I know, there's no plans to crash it into something, and they're gonna be so low that they can't get out of that gravity well to go somewhere else. So my guess is they just stop commanding it one day and it does whatever it's gonna end up doing. Question up front.
Yeah, the coal gas pressures, what kind of pressures are the coal gas, and then xenon also?
Yeah. So the high pressure system on both of those, about 2,500 PSI. So pretty high, pretty high. I mean, there's a lot higher pressure propulsion systems out there, but yeah, 2,500 PSI. And then you go through the feed system and you get to the pressure that goes into the thruster. And so with a cold gas system, that's about 300 PSI. So much lower. And then the Hall thrusters, they need 1 PSI going into them, 2 PSI, very low.
When you mentioned the Hall thruster, it expels positively charged ions, is that correct?
Yeah, you get positive charged ions coming out of the anode, and then negatively charged electrons coming out of the cathode. And then the cool part, it's a self-correcting thruster. So if it starts emitting more ions, the cathode, it'll pull more electrons with it. So unlike gridded ion thrusters, there's no way for it to charge up the spacecraft.
And charge imbalances that need to be corrected somehow?
Yeah, and all that happens within a couple of centimeters. It kind of self-corrects. But yeah, on gridded ion thrusters, something that NASA has a lot of experience, it has to have an extra cathode to neutralize the plume, otherwise the spacecraft would charge up, just due to how that thruster works. The Hall thrusters, one of the nice things about it is it doesn't have that problem.
How much energy does it use, and is there redundancy in the... Yeah, well, it's a NASA mission, so it's got lots of redundancy. That's a requirement. Zach may need help here. The solar arrays, I think, can generate like 25 kilowatts around Earth. Pretty high. That's a pretty normal communication satellite power level. And then Psyche is at 3 AU, so power decreases as 1 over AU squared. So the 25 kilowatts drops to like 2 kilowatts out of Psyche, 2.5, something like that.
Yeah, less than 10%.
Yeah, so it's a big range.
What was the mitigation for smaller asteroids impacting Psyche?
Yeah. Here's the answer everybody gives me. Space is big. At some point, that answer is not going to be true. But I think you get hit by an asteroid, that's a bad day. Right? I mean, it's just, right? Like, some of those are flying around at kilometers per second, and you get hit, you just, wow, sorry. I mean, the nice part is the spacecraft is designed so that you can lose bits and pieces of it here and there. We could lose a string on a solar array and continue with the rest. And little bits and pieces, it hits our spacecraft all the time, and sometimes it does stuff, sometimes it doesn't.
On the Hall thruster, you showed there's random blips on the thruster.
Yeah.
Do they give any trouble, and how do you handle those things?
Yeah, I'm kind of laughing because in some other development it's given us trouble. But these thrusters, I mean, credit to this Russian company called Falcon. They built a robust thruster. And the running joke is like you could hit it with a baseball bat, drag it behind a car, turn it on, and it would still work. But yeah, at 300 volts, that's a high voltage, but it's not that high. And so at 300 volts, you get these little bits of the thruster, like self-erodes itself, and the bits fly off, and you get this kind of blip in the current. The current goes up, the voltage goes down, recovers, and continues on its way. So for these thrusters, I'm not aware of any Hall thruster on orbit that's had a problem. We got some friends in the back from another company, and they launch a lot of Hall thrusters, probably more than we have at this point.
And they built some pretty robust thrusters as well, and I haven't heard any problems from them either. So yeah, the lower voltage, 300 volts stuff is pretty good. You get up to higher voltages, 600 volts, 1,000 volts, things can happen there.
I was wondering how many primarily metal asteroids, like Psyche, are there in the asteroid belt? Like larger ones?
I don't know. This is the only one that I'm aware of.
I think Lindy said that there are other ones, but this is by far the largest. So there's a dozen or so other ones, but they're a lot smaller. And another thing I was wondering about, did the war in Ukraine, in a way, interfere with the cooperation with the Russian company? Or?
Yeah, I mean, we can't talk with them. It'd be nice to say, hey, your thruster's doing this, tell me why. And now, we have to go figure it out ourselves.
But you still do business with them? Or
no, that's all done. Yeah, so I mean, the Russians invested 50 years ago in Hall thruster technology. Americans went a different route. We're playing catch up now for sure. But there's a host of American thruster companies now. I'd say for the propulsion world, a lot of xenon comes from that part of the world. And so the ability to get our propellants is a problem. Yeah.
To what extent the mission will say that the Psyche is part of a larger object or it is a separate object by itself?
Yeah, I mean, it's a good question. I definitely don't know the answer. I remember, Shane might need to help me out here too. I remember they came up with these possible Psyche theories, and they had like 4 theories at one point, and then they had 8 theories, and they said the asteroid may look like these 8 things, and we need to design the spacecraft for all of them. I think they really don't know what it looks like. It's kind of a blurry dot in the pictures that we've taken, so we really don't know. And the whole point of this mission is to go out there and figure it out. And my guess is there will be some of it that looks and you're like, yep, I expected it to do that. And there will be other aspects that are like, I had no idea. That's totally different from anything that I thought it could be. But I'm excited to see what pictures they come out with and the data.
So the Otter's conceptions are based on what, something from Star Wars?
Yeah. You don't give credit where credit's due. NASA does a pretty good job with the artist drawings. They got a quality team there in that department.
What is the plume on an electric propulsion like compared to like a chemical thruster? Does it cause any sort of attitude disturbance to it?
Yeah, so there's a lot less stuff. There's a lot less stuff, but it's coming out a lot faster. So for the chemical plumes, they're pretty hot, and they can heat up things if they run into it, and they can push against it. For this plume, it can also push against stuff if it's going to run into something, but it's coming out so quickly that it's running into stuff at really high speeds. So it slowly erodes things that it comes in contact with. The nice part about this mission is, you can't really see in here, but the thrusters are over here and they're firing outward, and there's really nothing there for it to hit. So far, and the hope is that there's no plume issues that we get, because there's nothing really for the plume to hit. We'll see if that remains true in a couple of years.
Yeah, are they constantly on, and do they have to slow down to get captured by the...
Yeah. I'll go back to that picture. So they are on, I think it's for something like 18 hours at a time, and then they turn off and they do some momentum management work, and then they turn on for another 18 hours. It's something like that. I don't know the exact time. It's like a day or so. But yeah, we're right now in this big gray thrusting arc, and so they're trying to get as high a duty cycle as possible. We'll get out of that, and then we're gonna kind of cruise on the way to Mars. I'm sure they're gonna have to do some adjustment burns to make sure they hit, the Mars trajectory just right to get that gravity assist just how they want it. And then there's another big thrusting arc That I think that'll be another about 18 hours on, off for a couple hours, 18 on again. Yeah, so the duty cycle is not that high. Yeah.
So this is a mostly, presumably metal asteroid, probably a lot of iron. Or magnet, like electromagnets that are considered to reduce the velocity that actually goes around.
Oh, that'd be cool. So, not being a scientist, my understanding, and Psyche is this way as well, is that the planetary magnetic fields are just tiny. I mean, just minute. The magnetic field that the thrusters generate is far, far higher. So I don't actually know if they would be high enough to really do anything. I know in Earth orbit we have torque rods and you can get magnetic torques and whatnot. So probably something like that is possible.
I mean, if the asteroids were heavily iron, wouldn't it just pull the spacecraft toward the asteroid?
Yeah, there may be, and I know.
That would be pretty risky.
Yeah.
There is no magnetic field there, and then you don't have anything. Right.
And we're actually still pretty far from the asteroid, like tens of kilometers away, so we're not close enough to really interact strongly that way.
Yeah, but I mean, looking at this picture that I know I made way too small so nobody can actually read it, but you got the three first orbits: orbit A in blue, orbit B in green, orbit C in red. Those are all pretty well defined. They're like thin lines going around. We think we have our act together on those. And then orbit D, the closest orbit, that's a really thick orbit because they know attitude control in that orbit is going to be hard. And that was one of that was most of the driving cases for what the cold gas thrusters needed to do, what the safe mode fault protection needed to do. That's a really tough orbit to stay in. And I think they're expecting a lot of gravity gradients and who knows what else. Rick?
Yeah, the gravity assist at Mars, what is that worth in terms of delta V?
Yeah, you know, I was thinking yesterday that same question, and I meant to look it up, and I have no idea. My understanding is it's quite a bit. It's a measurable percentage. Yeah.
So, given the communication delay is between 25 and 38 minutes, depending on where you're in orbit.
Yeah, right now.
Do you guys have an estimate for the communication delay at the time of rendezvous?
I think it's Shane, do you know it's a lot? Minutes, probably? Or maybe an hour?
30 minutes? Tens of minutes, but I'm not sure exactly.
Yeah. Yeah, I know the one of the big, when we were talking about safe mode, was that they had to be able to go into safe mode and have it stay there just forever, basically. I think it's like 3 weeks or 4 weeks at a time. Because it could take ground operators an immense amount of time to figure out how to command with it again and sort out whatever happened. But it's a pretty long time.
And what would happen if you guys get a communication blackout at the time of rendezvous?
Well, yeah, that's a problem. I mean, we've had a lot of
one way probably takes about 30 minutes.
Yeah, I mean, we've had a bunch of problems where like you command it to do something on a Monday. You go have a great week, you get back on Friday, and you're like, well, that doesn't look right. So we're using the Deep Space Network. And that's, I mean, the world has, as we have more of these missions that go out there, we have a bandwidth problem on that network. Psyche is struggling to get time on that network compared to everyone else who wants it. And as Maxar is launching another satellite in a couple of years that, you know, me and Propulsion, I'm saying I want constant communication with my thrusters nonstop, and they're like, well, you're going to get like 2 hours a day. So there's the Deep Space Network. There's a lot of articles online about how we're really stressing that, and we need more antennas around the world and whatnot. It's a problem.
So do you guys communicate through the Deep Space Network at Goldstone? Through the
There's 3 locations, right? I think we use all 3.
Spain.
Yeah, whichever one we can get time on, and where that's lined up with where the satellite is at that particular time.
And was JPL involved in the DSOC development, or it's you guys basically handled it?
It wasn't us. Was that run out of JPL?
It was, yeah.
Yeah.
It was a JPL project.
Yeah.
You were laughing when you pointed to the lures on the satellite.
Lure, yeah, there's
Is there
a
a
thermal
story
engineer
there?
sitting right there. She's a big fan of those lures.
Obviously, there's no convection up in the space.
Right.
Probably for the near conditions. The lures to manage the thermal loads.
How they work?
Why are they there?
Why are they there? Fair enough.
It's like a contingent charter thing, so if you want to reject those charters, they'll kind of like a spring kind of thing. And then if you want to keep it even inside within the first, that's going to keep it.
Yeah, I think they were described to me like a thermostat. They like autonomously open if it gets too hot, and then they autonomously close if it gets too cold, and they're calibrated for some temperature range.
Elephants actually do that too. Their ears, they
Elephants?
use it to regulate their temperature. By like
Fair enough. We'll put a giant elephant in space.
Yeah, we were talking earlier about redundancy. I was wondering about, so there's computer systems in the spacecraft bus. Is that redundant?
Yeah, just direct that question to that guy sitting right there. Yeah?
Oh, yeah, for redundant process movements. Yeah.
I don't even know what those words mean. That's good.
Like, how much xenon is on there, by the way? How long will it last?
We loaded, the requirement was to load 1,085 kilograms. And I remember we got there and then we said, anybody around? Let's put a little bit more in there. So there's 1,085.5 kilograms when we launched. I think we've used about 40 or 50 kilograms so far. So we still have over 1,000 kilograms. And I mean, it's a NASA mission. They put margin on top of margin. So we should get to the asteroid with 200 to 300 kilograms left. It'll be interesting to see what that number actually looks like. Running out of xenon before we get there would be a very bad day. But I think we got a ton of margin on that number.
Squeeze the handle.
Yeah, right.
I wanted to ask, what is the degree of autonomy that the spacecraft has, and how much is it controlled by the ground in comparison?
No, Shane, what do you think?
I mean, it's entirely autonomous, right? All the sequences that are needed to operate the spacecraft have to be on board because you can't control it from the ground. I mean, as soon as we launched it, within days it was, minute delay, 2 minute delay, 3 minute delay. You can't really command the spacecraft, with that kind of delay on the ground. The ones that we launch at GEO, we've got a couple second delay. We control those from the ground, but even those have autonomy built in. But Psyche is entirely autonomous. It has its own sequences. From the ground, you can tell it what you want it to do over the course of the next week as its primary operations, and it'll do that. But it'll do it by itself, and then it'll turn back to Earth in a week and tell you how it did.
So I don't know if you know the answer to this, but with the ESOC system, so you said, it's dependent upon having good weather day in SoCal to receive the transmission from there. Do you know by any chance if there's any plans to put something in orbit to be able to receive it?
That'd be cool. I don't think there is, not for this. I know they're fighting right now because the DSOC mission, it ends in a couple of months, and so they're fighting right now just to get more money to keep it going later. Which I assume they'll be successful on because you want to use that out at Psyche. I'm sure they'll try and beam something from there. But yeah, a receiver station in low Earth orbit makes a lot of sense. Future technology for communication or power beaming or all kinds of stuff. Getting up above the weather out of the atmosphere would help solve a lot of problems.
Is there anything about some of those other asteroid mining companies that you want to say and can say?
Anything about them?
Yeah.
I got a lot of friends who worked for them, and then they've closed their doors, changed their name. It's such a cool idea. But when the return on investment from that is just decades. And the amount of technology you got to put in up front, I mean, it's like, it's hard to have a legit mining operation here on Earth. Now you got to go do that somewhere else. So I'm excited at the opportunities of that. I think there's been a lot of companies that have made a lot of PowerPoints and talked a lot, and then they're like, well, we need $1 billion, and they don't have $1 billion. So I think it's tough, but that's one of the areas where larger launch vehicles launched more often. There's a lot of asteroids that come very close to Earth. You know, it should be relatively easy to go get close to them, to land on them, and with Starship or New Glenn. I guess SLS as well, you can put a lot of mass in orbit. And so there's kind of the next 10 years, 15 years should be pretty interesting to seeing what stuff people can put up there. But I don't have any inside information about those companies and whatnot. But there's a lot of, I think the ROI is long, but there's a lot of money that could be made. Any last questions?
Just out of curiosity, when you were at JPL, did they feed you with the peanut? They have a peanut culture.
The peanut, yeah. There were a couple people in mission ops that had a peanut allergy. And it was like a whole thing. People were throwing peanuts around. I'm like, that person could die right now. They do the peanut thing. I like heard of it before, but some of their old timers take that really seriously. I was like eating the peanuts too early, or I didn't finish all of them at the right time. I got yelled at. That's
pretty old tradition, since like the early.
A long time ago. Yeah.
Is Maxar still at the mission control table right now, or is it solely NASA operating Psyche?
I don't know. I'm in a lot of meetings. I feel like I'm still pretty involved, but yeah, we don't go down there that much anymore. We were there a lot right after launch. And the questions are still coming in, but it's really a JPL run thing now.
So is NASA asking for more missions from Maxar?
I hope so. It keeps me employed. Yeah. We'll see. Cool stuff. All right. Thanks, Eric.